Yesterday morning, the physical laws governing one of the planet's most volatile tectonic structures were momentarily rewritten. In the span of just 60 seconds, the floor of the Pacific Ocean broke apart twice. It began with a magnitude 6.0 rupture, striking 156 kilometers east-southeast of Petropavlovsk-Kamchatsky. Before the initial seismic waves could even disperse, the same narrow corridor of the seafloor ruptured again, this time releasing a far greater surge of kinetic energy at magnitude 6.6. Under standard seismological models, massive earthquakes are isolated events, followed by a predictable decay of smaller aftershocks. What occurred off the coast of the Kamchatka Peninsula was an earthquake doublet. Two major shocks of nearly equivalent scale occurring back-to-back, virtually on top of one another. It is a profound mechanical anomaly that immediately commanded the attention of global monitoring agencies. A doublet indicates that the initial failure of the crust did not resolve the systemic load. Instead, the stress was instantly transferred along the fault, with the first rupture actively loading the adjacent segment to its breaking point. This is the direct physics of stress redistribution, comparable to pulling a single log from a jam and instantly transferring the entire weight of the river onto the next. By 6 minutes past 7 in the morning, just 1 minute after the second rupture, automated emergency networks issued a high-priority tsunami warning centered near the Commander Islands, broadcasting across the North Pacific. The system acted on a hard logistical rule. When a violent shallow rupture occurs beneath the ocean floor, there is no time to wait for direct observation. For communities living along these coastlines, a wave can arrive in minutes, and the system must err toward absolute caution. Yet, shortly after the sirens began, the ocean remained flat. The warning was terminated, leaving behind what appeared to be a stark physical contradiction. The explanation lies in the exact geometry of the slip. While the catastrophic historical ruptures of this region thrust the seafloor vertically to displace the entire water column, yesterday's doublet likely slipped sideways, leaving the overlying ocean largely undisturbed. But this reprieve is a function of geometry, not a reduction in the regional threat. The true scale of this crisis is anchored in the geography of the Kuril-Kamchatka Subduction Zone, a massive tectonic engine where the Pacific Plate slides beneath the Asian continent at a rate of 80 millimeters per year. This is roughly the speed at which human fingernails grow. But over decades, this slow creep bends the locked rock like a giant spring, winding it tighter with every passing year. Directly above this locked boundary sits Petropavlovsk-Kamchatsky, a dense urban center of 180,000 people. Following the doublet, the fault began to discharge its stored energy not in a slow taper, but in a relentless barrage. Before noon, more than a dozen earthquakes of magnitude 4.5 or greater battered this localized patch of the seafloor. Even a single 4.5 magnitude event is capable of structural damage in populated areas. Here they were stacked continuously, repeatedly punishing structures weakened by the initial shocks. The true abnormality of the sequence was revealed when a magnitude 5.8 shock struck late in the morning. In a typical decay sequence, aftershocks lose amplitude over time as the system stabilizes. A major shock occurring so late in the sequence proves that the fault still has immense reserves of energy to give, shattering any immediate hope of stabilization. This brings us to the fundamental mechanical question confronting researchers today. If the first major rupture triggered the second, what physical mechanism prevents the second from triggering a third catastrophic failure? We are forced to look directly at the ultimate capacity of this subduction zone. The baseline of this system is not defined by magnitude 6 events. The last time this exact fault fully released its locked energy was in November of 1952, when it produced a magnitude 9.0 earthquake, generating a devastating tsunami that decimated the town of Severokurilsk and crossed the entire Pacific to flood the coastlines of Hawaii. That historical reality removes all abstraction from the current data. The doublet has demonstrated in real time that these fault segments are actively communicating, passing stress from one block to the next. As the aftershocks continue to rattle the Kamchatka coast, we are left suspended in a critical window of observation, waiting to discover if this violent sequence is merely the fault settling down, or the final warning sign before the entire system gives way. To understand the human and structural stakes of this modern seismic crisis, we must look at the long-term cycle of the Kuril-Kamchatka Subduction Zone. This is what geophysicists call the quiet trap of a long earthquake cycle. Over decades, prolonged tectonic silence has allowed a major modern city to expand directly above the fault line. Petropavlovsk-Kamchatsky now holds far more residents than it did during the catastrophic event of 1952. For most of these people, the worst-case scenario exists only as historical record, not personal memory. But a continuous barrage of aftershocks strips away this complacency. Unlike a single earthquake, which ends in seconds and allows immediate structural assessment, a prolonged seismic barrage acts as a corrosive force. It creates a state of continuous vulnerability where buildings cracked and weakened by the initial doublet are subjected to repeated physical stress. With every successive aftershock, the cumulative damage mounts, and the minor fractures in concrete and masonry are driven to complete structural failure. This physical toll is mirrored in the human population, who must endure the psychological pressure of an unanswered question: is each new tremor the end of the sequence, or the beginning of a larger rupture? To determine where the bottom of this sequence lies, seismologists rely on the strict mathematics of aftershock patterns. These empirical laws are not predictive tools, but running statistical forecasts updated by the hour. The first rule dictates that aftershocks decay over time in a highly predictable curve, firing rapidly at first before gradually tapering off. The initial dense flood of earthquakes off the Kamchatka coast conformed precisely to this decay model. However, the second rule introduces a troubling outlier. This rule states that the largest aftershock in a sequence typically measures between 1 and 1.25 magnitude units below the main shock. For a magnitude 6.6 event, this formula predicts a maximum aftershock of approximately 5.4 or 5.5. The occurrence of a late-stage magnitude 5.8 earthquake violates this statistical boundary, running hotter than expected and signaling that the fault segment is struggling to stabilize. While the third rule, which describes the proportional relationship in number between earthquakes of varying magnitudes, matches the standard distribution of a normal subduction zone sequence. That single 5.8 anomaly keeps the scientific community highly guarded. As the ground continues to move, public anxiety inevitably breeds alternative narratives. In the modern information space, claims of external triggers spread rapidly, yet they collapse under the weight of basic physical laws and energy budgets. The assertion that this doublet was triggered by solar activity is instantly invalidated by observational data. The sun was entirely quiet on the day of the rupture, with no significant coronal mass ejections or solar winds directed at Earth. More fundamentally, there is no established physical mechanism that can translate space weather into the mechanical breaking of deep lithospheric plates. Similarly, theories of a global surge in earthquake frequency are debunked by long-term global seismic baselines. The annual rate of major earthquakes has remained remarkably steady for over a century. What has changed is not the Earth's activity, but our modern sensor networks and the instantaneous global transmission of seismic data. Finally, the narrative of anthropogenic or machine-engineered intervention is rendered impossible by the sheer scale of the energy released. The kinetic energy discharged by a single magnitude 6.6 earthquake dwarfs the maximum energy output of any human technology. This was a purely natural release of stored tectonic force. The true engine remains the silent, relentless descent of the Pacific Plate beneath the Asian margin, progressing at 80 millimeters every year. Because we can neither control this process nor predict the exact moment of the next slip, mitigation relies entirely on human readiness. The lesson carved into the history of the Kuril Islands in 1952 is brutal but clear. In the immediate vicinity of a subduction zone, the physical shaking of the ground is the only warning that matters. If the Earth moves violently enough to disrupt balance, or if the shaking persists over a prolonged duration, coastal populations cannot wait for official broadcast alerts. Near the epicenter, the tsunami waves will outrun the digital warning systems. The earthquake itself must be treated as the evacuation siren, prompting an immediate retreat to high ground. As seismologists continue to monitor the fading or escalating rates of the Kamchatka sequence, this fundamental protocol remains the primary line of defense against a fault that has already proven its capacity to devastate an entire ocean basin. The current state of the Kamchatka Peninsula is defined by a critical temporal window, the foreshock interval. In the immediate aftermath of an earthquake doublet, geophysicists do not merely analyze the past. They calculate the statistical probability of what might follow. Across the global seismic record, there is a small but mathematically real probability, measuring only a few percentage points, that any major rupture is not the main event, but a foreshock. When a doublet occurs, this small probability ceases to be an abstract mathematical detail. It becomes an immediate operational concern. The physical reality of a doublet is that the regional stress field has been dynamically altered. One segment of the fault has slipped, shedding its load and transferring that immense mechanical strain directly onto the adjacent locked patches. This stress transfer can act as the final trigger for a neighboring section that is already highly pressurized, potentially initiating a cascading failure along a much larger portion of the plate boundary. This is the shadow of 1952. When scientists look at the Kuril-Kamchatka Subduction Zone, they are guided by the physical parameters of the magnitude 9.0 earthquake that ruptured this exact margin. That event demonstrated the absolute physical limit of this tectonic system. It did not merely shake the local peninsula, it displaced an entire ocean basin, generating a tsunami that destroyed the town of Severokurilsk and retained enough kinetic energy to travel thousands of kilometers across the open Pacific, causing severe flooding and tearing vessels from their moorings in Hawaii. Today, the stakes are exponentially higher. The decades of relative calm that followed the 1952 disaster allowed the regional population to grow, with Petropavlovsk-Kamchatsky expanding its infrastructure directly over this active subduction interface. This expansion exposes the core paradox of seismic hazard mitigation. The longer a fault remains locked and silent, the more vulnerable the modern civil infrastructure becomes, and the greater the potential loss when the system inevitably slips. Consequently, the immediate scientific objective is to closely monitor the evolution of the aftershock sequence over the critical days following the doublet. Seismologists are tracking the hourly decay rates to determine which path the system will take. If the frequency and magnitude of the aftershocks steadily decline on schedule, it indicates that the regional crust is absorbing the stress transfer and settling back into a stable, locked state. The doublet will be recorded as a violent but isolated release of localized strain. However, if the decay rate plateaus, or if a new highly energetic rupture occurs that rivals or exceeds the initial shocks, it will serve as a direct physical signal that the system is escalating. With each quiet hour that passes without a major secondary rupture, the probability of a catastrophic larger event narrows. But this fading probability does not mean the danger has dissolved. The fundamental driver of the crisis remains entirely unchanged. The Pacific Plate continues its relentless, silent descent at 80 millimeters per year, constantly winding the lithospheric spring. The doublet of yesterday was not an isolated incident, but a stark demonstration of a planetary machine that is still fully loaded, still accumulating strain, and still entirely capable of unleashing the ocean. For the researchers monitoring the data streams, and for the global communities lining the Pacific Rim, looking away is not an option. The resolution of yesterday's seismic event brings us back to the primary physical mechanism of the ocean itself. To fully deconstruct why the tsunami warning was stood down without a disaster, we must examine the micro-level dynamics of seafloor displacement. When a subduction zone fails catastrophically, as it did in 1952, the fault boundary undergoes thrust-slip motion. One massive block of the crust is shoved violently upward, lifting the entire overlying column of seawater and initiating a deep ocean gravity wave that travels at jetliner speeds. Yesterday, however, the physical indicators suggest the seafloor underwent a different mechanical displacement. The ground slid predominantly sideways. Because horizontal movement does not vertically displace the water column, it fails to pile the ocean up into a wave. The system spared the coast not due to any dissipation of tectonic energy, but because the directional orientation of the slip fell on the safe side of a highly volatile line. This highlights the limits of automated monitoring. The warning systems functioned flawlessly, acting immediately on the shallow depth and magnitude of the doublet. But the raw sensors cannot immediately map the precise slip vector of a rupture in the opening minutes. This mechanical delay reveals a profound systemic truth. Technology is a secondary layer of defense. The primary warning system is the Earth itself. For the population of Petropavlovsk-Kamchatsky and the broader Kuril-Kamchatka coast, waiting for a digital broadcast is a critical failure point. If the ground shakes continuously, or with an intensity that prevents standing, the physical event is the only signal required to retreat to high ground immediately. This direct human protocol is the real-world application of historical data. The tragedy of Severokursk in 1952 was a brutal demonstration of this rule. The modern expansion of Petropavlovsk-Kamchatsky, now housing 180,000 people, means the spatial density of human vulnerability has increased dramatically. Decades of seismic quiet have allowed residential and civic infrastructure to settle over a plate boundary that is actively accumulating strain. This brings us back to the ongoing statistical evaluation of the aftershock sequence. Seismologists are operating in a state of high watchfulness, continuously processing the incoming magnitude data to map the stress state of the fault. The occurrence of the late-stage magnitude 5.8 aftershock remains a key point of analytical friction. It shows that the crust has not yet returned to a state of equilibrium. While the overall frequency of the smaller shocks continues to align with standard decay curves, that single energetic rupture indicates that the local stress fields are still actively shifting. Ultimately, this sequence forces us to confront the hard limits of the Earth's most powerful systems. The theories of external triggers, whether solar or anthropogenic, fail because they ignore the absolute scale of tectonic energy. The Kuril-Kamchatka Subduction Zone is a self-contained geophysical machine, driven by the slow, inexorable descent of the Pacific Plate into the mantle. The 80 millimeters of movement accumulated each year represents a physical debt that must be settled. The doublet of yesterday was a minor adjustment along a massive boundary, a momentary relief of localized pressure that may have loaded adjacent, larger segments of the fault. As the scientific instruments continue to record the declining tremors, the immediate crisis may fade, but the fundamental structural load remains. The spring is still winding, the plates are still grinding, and the deadly fault off Kamchatka remains fully locked, waiting for the next inevitable fracture. As the hours stretch into days, the ultimate trajectory of the Kamchatka seismic sequence becomes clear. Seismologists watching the incoming data streams observe the gradual deceleration of the aftershock rate. The dense barrage of tremors that characterize the immediate aftermath of the doublet is slowly conforming to the mathematical decay laws, tapering off as the fault segment struggles toward a temporary equilibrium. This reduction in activity is a relief, but it also highlights the profound limits of our observational science. Seismology does not possess the capacity to predict the exact moment of a future rupture. It can only map the current state of stress and calculate statistical probabilities. The temporary decline of aftershocks does not mean the threat has evaporated. In the physics of subduction zones, a quiet fault is not a safe fault. It is a locked fault. The convergence of the Pacific and Asian plates continues at its immutable rate of 80 millimeters per year. This constant forward movement means that even as the local crust settles, the geological spring is immediately being wound tighter once again. The doublet was not a systemic reset. It was a localized fracture in a machine that remains fully loaded. To analyze this crisis at its deepest level, we must confront the stark contrast between human timelines and geological reality. Decades of seismic silence along this portion of the Kuril-Kamchatka margin allowed a modern urban infrastructure to expand, placing 180,000 people directly above an active plate interface. This is the quiet trap of the earthquake cycle, where the absence of a disaster in recent memory is mistaken for its permanent removal. The doublet of yesterday shattered this illusion, forcing a direct confrontation with the physical boundaries of this system. It proved that the segments of this fault are in active physical communication, capable of transferring stresses across massive distances to trigger successive failures. While the sideways motion of this specific doublet prevented a devastating water displacement, the historical precedent of 1952 stands as a reminder of what happens when the fault thrusts vertically. The magnitude 9.0 earthquake of 1952 was not a theoretical modeling exercise, but a physical reality that wiped out Severokurilsk and sent a high-energy tsunami racing across the entire Pacific to Hawaii. That capability remains entirely intact. This reality exposes the true boundaries of human technological intervention. We cannot engineer the crust, nor can we alter the mechanical forces driving the subduction of the Pacific plate. Our advanced sensor networks, automated tsunami alerts, and statistical decay models are vital diagnostic tools, but they are entirely passive. They do not prevent the rupture. They only record its consequences. Ultimately, the survival of coastal communities relies on recognizing these hard limits and adhering to the primary physical warning of the Earth itself. When the ground shakes violently, there is no time to wait for a digital broadcast or an official siren. The physical movement of the crust is the definitive evacuation order. As the monitoring stations record the final, fading tremors of yesterday's sequence, the immediate alarm stands down and the sea remains flat, but the physical budget of this plate boundary continues to accumulate. The spring is winding, the plates are grinding, and the deadliest fault in the Pacific remains locked in place, silently loading the energy for the next inevitable failure.